Let's do a couple more examples of the quotient construction. Again, all the verifications are by the first isomorphism theorem. So here it is again quickly. Let's say psi is a onto ring homomorphism from R to S. R and S are rings. You have the natural quotient homomorphism from R to R mod the kernel of psi. Statement is that given any psi, it induces isomorphism from R mod the kernel to the image. Called it eta. So in particular, if you have a surjective ring homomorphism from R to S, then R modulo the kernel of the homomorphism is isomorphic to the image of the homomorphism. Okay. We looked at Z mod n. Let's look at the other principal ideal domain that we know, fx. In fact, we can just look at real polynomials. So the ring that I'm going to look at would be one variable polynomials with coefficients in real numbers. And we could take anything else, but this is good enough. You could replace R by other fields. So the ideals in this ring look like multiples of a single polynomial. So let's pick a single polynomial. Fx equals a0 plus a1x plus in x to the n be a polynomial of degree n. Well, maybe it would be somewhat cleaner if I just make it monic. So, meaning the top degree coefficient is just 1. So let's look at R mod f. If you want to write it longhand, single variable polynomial modulo all multiples of this single polynomial. So my claim is that the elements of this ring are in one-to-one correspondence with the polynomials in R of degree at most n minus 1, meaning degree less than that of f. So this, I've written out a sketch. Let me just say briefly what's going on. Let's call this quotient ring S. And you have the natural quotient map, right? From the domain to S, quotient map. If you give me a polynomial g, then the coset of it, it takes it to the coset. Right. My claim is that this coset is same as the coset of R, where R is the remainder when you divide G by F. R is the remainder when G is divided by F. Because you see, you can divide G by F and you get a quotient and a remainder, and then the difference of these two guys, Gx and Rx, is a multiple of F, you see. So the coset of G is the same as the coset of R. So what this tells you that every coset in S can be represented by one of these remainders. And what do we know about the remainders? Note that the degree of the remainder is less than degree of F. So every element of S is of the form R plus F, where R is a polynomial of degree at most n minus 1. And now I have to show that if you have two polynomials of degree at most n minus 1, they give you different cosets. So the cosets are in one-to-one correspondence with these polynomials of degree at most n minus 1. Okay, so concretely, you can think of elements of this quotient ring as polynomials of degree n minus 1. When you add them, you just add them. When you multiply them, sometimes you might get things of degree more than n. But then you divide by F and take the remainder, and you have again brought the degree down to less than n. That's how the addition and multiplication of this ring works. So elements can be represented by polynomials of degree up to n minus 1 if R1 and R2 are two such polynomials. Then when you multiply them, you just take multiply, it's R plus, let's put it this way, it's R plus F, where R is the remainder when R1 times R2 is divided by F. This is exactly like Z mod n.